So next, we are going to look at the angle of departure and arrival at complex poles. Okay, so this is the third step in the refining of the root locus. The first, we looked at breakaway and breaking points from the real axis. The second, we looked at the j omega crossing, okay, and we saw that you have to use the route Howard's criteria and the closed loop transfer function to find the values of k for which it crosses the imaginary axis. And since those values form the boundary between the stable and unstable poles, then we can easily do this, okay, by forcing a 0 on a row, okay, and once we force that 0 on an odd power row, then we form the auxiliary equation, which is going to be an even polynomial, and we solve that for the roots, hopefully to get our j omega crossing points. Now, the next thing is, if we have a system with complex poles, how do we also deal with that? So let's take a system with G, K, G, H equals K into S plus 2 all over S plus 3, S squared plus 2S plus 2. And then we'll see that the zeros will be equal to minus 2, okay, and then the poles, that is the number of zeros, equals 1, and then the poles will be equal to minus 3, that is a real pole, and then we are going to have minus 2 plus minus square root of 2 squared minus 4 into 2 all over 2 times 1, okay, which gives us minus 1 plus minus j1, okay. Minus 1 plus minus j1, okay. Okay, so this is because what is under the root sign is going to give us 4 minus 8, which is square root of minus 4 all over 2, which is equal to square root of minus 4 over 4, and that is j1. Okay, so this will give us the root. So you see that the poles are 3, so the number of poles equals 3. Okay, so if you want to plot the root locus, okay, so I can have my 1, 2, 3, 4, minus 1, minus 2, minus 3, minus 4, okay, so 1, 2, 3, 1, 2, 3, this is minus j, minus j, minus j1, and then this is j1, j2, j3, okay, j omega axis, and this is the sigma axis. So with this system here, now let me plot my zeros and poles. So my 0 is at minus 2, no problem, and my pole, I have one at minus 3, and I have another one at minus 1 and 1, okay, and another one at minus 1 and minus j1. So this will be my 2 other poles, okay. So the question then is, what will be the angle of departure from these poles? Well, it's very simple. We are going to, so already if you plot the root locus, we will know that, 1, okay, so if you plot the root locus, this is 1, 2 on the real axis. So here is going to originate from and ends from the pole and ends on the open loop 0. Okay, then there will be 2 root locus which will be originating from these poles and departing from, they will depart along some lines, okay, asymptotic lines. So let's find the asymptote. The centroid of the asymptote will be equal to the sum, okay, so the imaginary part will cancel out. So the poles will be -3, -1, -1. So -1, -1, -3. Okay, that will be summation of the poles minus summation of the zeros. And the 0 is -2. Divided by the number of poles, 3, minus number of poles, 1, of zeros, 1. And this is going to give you -5 plus 2 over 3, which is -3 over 3, over 2. Over 2, which is -1.5. Okay, so we have -1.5 point here, and this, and the angles, you can compute the angles. So the angles, theta, will be equal to 2k plus 1 times 180 all over 3 minus 1, and that will give us 2k plus 1 times 90. Okay, so when k equals 0, we have 90, k equals 1, we have 270. Okay, so those will be the angles. So you see that this will be the asymptotic lines, which means this pole will depart from here and then move along this angle of asymptote, and this one will depart from here and move along this line of asymptote. Okay, to clear the confusion, let me use different color for the asymptotes. Okay, so they are not part of the root locus, the roots. They are just lines that the root locus will never cross as it moves towards infinity. So now the question is, what will be the angle of departure? So this angle, we are interested in this angle. Is the positive extension, this angle. Okay, and we are interested in, if we come down here and you draw this, actually we are interested in this angle. Okay, so it's evident that the sum of these two angles equals 360, right? And that's because they are complex conjugates. Of course, the sum of the two angles will be 360. Okay, so let's try to find the angle above. Okay, let's try and find the angle above. And then once we know that, we'll be able to find the angle. Okay. So what will be the angle of departure? Well, what we can do is that we can find a small point, a point that is very close to this root, this pole, but lie on the root locus. Okay, and then once we find that point, then we'll be able to use that point for our computation. Okay, so let's look at what we can do with such points. So come down here. Okay, so let's pick a small point there, and we are going to have some angles. Okay, so if we pick a small point here, what we are going to look at is the angular contribution of this. So that will be theta. Let me call it. This will be angular contribution of this. Okay, that will be another theta. Then the angular contribution of this. This will be theta. Okay. Then the angular contribution of the pole here, which is also very close to that point, that is also going to be theta. So let's call this theta 1, call this theta 2, call this theta 3, call this theta 4. Okay, so what we know from above is that the summation Okay, so the summation of these angles should be equal to 180, right? That's what we know. Okay, so it means that we should find the angle such that the summation of these angles will be equal to 180. So what can we do about that? It's very simple. If you look at it critically, you see that our theta 1, okay, so minus theta 1 minus theta 2 plus, because it's an angle of a contribution from a 0, plus theta 3 minus theta 4 should be equal to 0. Okay, so that is basically it. So it means minus theta 1 minus theta 2, or to write it in the form we have, summation of 0, the angles of zeros, minus summation of the angles of poles should be equal to an odd multiple of 180. Okay, so we will just select 180 as our, and then the angles of the zeros summation will be, the 0 angle was what? Well, that is theta. If you come here, it's theta 3. So theta 3 minus theta 1 minus theta 2 minus theta 4, okay, should be equal to 180. Or if you want to be more conservative, theta 3 minus theta 1 plus theta 2 plus theta 4 equals 180. Whichever you are comfortable with, you can use. Okay, so let's find theta 3. Okay, so theta 3 is going to be the angle here. Okay, so this point is at, so if you draw it, it's forming something like this. Okay, okay, where we have this point, which is minus 2, that's where the 0 is, and this is minus 1, and this is J1. So we are finding this angle theta. Okay, so immediately it tells you that it's going to be tan inverse of TOA, opposite over adjacent, and the opposite is going to be, this is 0 line, so the opposite is going to be 1 minus 0 over the adjacent, and the adjacent is going to be 2 minus 1. Okay, that will be giving you this angle. Okay, so that immediately tells us it's going to be, the theta 3 will be tan inverse of 1 minus 0 all over 2 minus 1. Okay, minus, okay, so we are going to find theta 1. So you come up here, what will be the angle? Theta 1. Okay, so theta 1 is then going to simply be what we are looking for, so we don't know. Okay, and then plus theta 2. What is the angle theta 2? Because they are complex conjugates, theta 2 is 90 plus theta 3. Where is theta 3? Theta 3 is this point, so that one also looks like this. This is 0, and this is the point. Okay, this is 1, so minus 1, and this is minus positive J1. Okay, so it means that you have a point here, your theta is minus 3. So there again, we are going to have tan inverse of the opposite, which is 1 minus 0, over the adjacent, which is 3 minus 1. Okay, we are using magnitude because we just want the magnitude of the angle here. Okay, so once you do that, then that is going to give you tan inverse of 1 over 3 minus 1. Okay, so this is basically what expression you are going to get. Equate it to 180 and solve. Okay, and this is basically going to give you 45 minus theta 1 minus 90 minus 26.56 equals 180, and so theta 1 equals 180 minus 2 180, so you bring, sorry, so it's going to be 45 minus 90 minus 26.56 minus 180. Okay, and if you do this, what is that going to give you? Let's point it. So 45 minus 90 minus 26.56 minus 180, and that is minus 51 or 251.56. Okay, and I can add 360 to this. If I add 360 to an angle, I've not done anything. Okay, and if I add 360, so plus 360, that gives me 108.44. So we have two angles. Okay, one angle is this, one angle is that, the other angle is this. Okay, the reason why I got this is because I was using those positive angles. Anyway, so this tells me that the angle of departure from the real or the complex roots will be theta 1 equals, as we found, minus 251.56, and theta 2 equals 108.44. Okay, so you can theta 2 equals and theta 1 equals, it doesn't matter. So the angle of departure, they are going to be always 2, and one is this, one is that. Okay, so those are the two angles of departure. Okay, of course you can add 180 to this to get that for the other angles, whichever way you want to do it. So these are the two angles of departure. Okay, let me not confuse this. Okay, so the angle of departure theta 1 is equal to this, which is equal to this, and what I'm saying is that theta 1 plus theta 2 should be 360, and therefore our theta 2 should be equal to 360 minus 108.44, which is going to be equal to 251.56. Okay, so that's basically what I'm saying about those angle of departure and angle of arrival. So that will bring us to the end of how to compute the angle of departure and angle of arrival, the third video on refining the root locus. Thank you.